Okay, so good morning everyone. Welcome to the last day. So in the first session, we have 5 talks today. And interestingly, all 5 talks will feature scalar fields as inflaton, dark energy, and dark matter. So we start with Kazu's talk. Over to you.
Okay, I would like to thank the organizers, especially Diraj, for hosting this wonderful meeting. There have been so many interesting talks and discussions. I'm really happy. I'm really enjoying the meeting. So today I'll talk with this title, Cosmology Models Outside the Swampland. So yeah, swampland may sound a little bit exotic, and I feel it a little bit challenging to make you interested like me, but I'll try to explain that it's a decent thing to do, and yeah. So today the time is limited, so I'll focus on how string theory motivates models. So it will be review and some case study. But as a whole program, we would also like to make a prediction of the model to observations. And for that, there is a work by Vignesh sitting there, a poster. So please ask him about this part. And after making model predictions to observations, you would like to test with cosmological data. And for that, later you will hear about that from Sweder, former PhD student, and right now NPDF at IIA with Pravar, and Kanan, Pravar's student, also working on this part. And so I think previously some of the researchers were motivated by swampland. That is encouraging. So yeah, this is about the universe, and you have seen many times, and I'm just showing this to motivate particle physics model of inflation. So universe started at such a high energy and density. We need elementary particle physics to describe it. So that introduces us to think about what is particle physics. So particle physics is described by quantum field theory. And basically everything is measured by energy scale. Length is inverse of the energy, momentum is energy unit, etc. So we talk about energy. High energy means higher energy means shorter distance, right? And current standard model of particle physics can describe around 10 to the 3 GeV or so, giga-electron volt. And there are theoretical reasons that we expect it to be modified a little bit above that. And above that, we have scarce data to know what is particle physics describing this higher energy. And simply extrapolating, the quantum gravity is expected to be relevant at around 10 to the 18 or 19 GeV. I'm using so-called reduced Planck's mass, which is a little bit smaller than the standard Planck mass, and which is more convenient for particle physics. So yeah, so there's a huge gap between this quantum gravity scale and the scale we currently understand. So I'm trying to guess what is happening here is really, really challenging thing. And so how to know the physics, particle physics beyond the standard model? One is top down. So assuming that fundamental principle and trying to define the theory at the shortest fundamental scale and trying to make a prediction. And of course, so it's really hard way. And another approach is bottom up, which is more modest. So you know this part, and based on the knowledge you have, you try to differentiate from the lower energy. And so yesterday we heard about effective field. So effective field theory is a suitable framework for bottom-up because effective field theory is a theory limitation. So it has a highest energy cutoff, because UV cutoff. So above which this theory or certain is known to break down, and that is fine. This theory can describe well anything below this cutoff scale. It's arbitrary good precision you have, you want. So basically, effective field theory is a power physics expansion in terms of E over cutoff scale, where E is the energy of your interest. And energy of your interest is always below cutoff scale. So yeah, this term will go smaller and smaller as n integer n becomes larger. And this can also be used to discuss whether some parameter values are natural or not. And so for given particle contents and symmetry, we write down all possible terms in the action. So you can see this is the most general framework to describe the physics below lambda UV cutoff. And the foundational theorem for effective field theory is this decoupling theorem. This is basically saying, so if there's a theory which describes the higher energy scale, more fundamental theory, even though it exists, their effect at low energy is only to shift parameters of the low energy effective field theory. So that means if parameters are fixed experimentally, you don't need to calculate it from fundamental theory. So you really don't need UV theory. Yeah, so yeah, if you know the particle contents and symmetry, this is all you need to describe elementary particle physics below lambda UV. And so yeah, effective C theory is such a nice framework. So you see a lot of people who really love it. So during the COVID time, for example, those people are having online meeting, and you can see they really love this effective field theory. And I think many of them have this kind of view. So at some energy scale, you have effective field theory 1, which can describe the physics below lambda 1. So above that, what will happen? So above that, there's another effective field theory 2, which can describe the physics at this energy scale. And that will also break down at some energy scale. And then it goes on, goes on, goes on. You can continue almost forever. Well, even then, actually, Planck scale is a little bit special. So quantum gravity is a little bit special, and probably effective field theory cannot be used above quantum gravity scale. So now I change the direction. So now the top-down approach. So top-down approach, so now I replace quantum gravity with string theory, which is the most promising candidate for the unifying theory of all the forces in nature, including quantum gravity, consistently. And this has a typical energy scale, or length scale, string length scale, or 1 over string scale is energy scale. And so you try to make prediction. Well, you can observe. So now, let me explain some relevant elements of string theory with this one slide. So in string theory, different particles come from different oscillation modes of the same string. So this is a unification. All the particles in nature coming from single string. And also, importantly, those particles comes as a set. So you start from string theory. You cannot choose, I want this particle, but I don't want this particle. No, if it is in the string oscillation, you have to have all of these. That's one important feature of string theory. And for theoretical consistency, predicts one time dimension and 9 space dimensions. But the world we observe is only one time dimension and 3 space dimensions. So there are 6 extra dimensions. So those are supposed to be compactified, meaning you cannot resolve it in the current experimental method. And low energy, they are roughly reduced to supergravity or super mu. Here, super has a special meaning, not just super means symmetry, which exchange boson and fermions. So, but string theory can also have extended objects, something called Dirichlet plane, D-plane, or Getford plane, etc. So these are specially extended objects, and you can use them to build your low energy model. And also, string theory doesn't have any tunable parameters. Parameters of low energy effective field theories are dynamical fields that take some constant values at low energy. And I'd like to mention that theory is not complete. The situation is a bit like old quantum mechanics. You have some theoretical framework in the old time, but we still don't have modern version of quantum mechanics. So we can do something, but something we can't do. But with some controlled approximation, researchers have found that string theory has a lot of minima of the potential energy. So phi 1, phi 2 are scalar fields. String theory can have a lot of them. And the potential energy is described like that. So it looks a little bit like a mountain. So that's why it's called landscape. And bottom, so if you can excite only the low energy, the bottom is described by, and yeah, depending on the parameter value of phi 1 and phi 2, the parameters or even the field contents in each vacuum are different in different theories. So this landscape of string theory vacuum motivated people to think that any effective field theories may be embedded in string theory. But then, around 20 years ago, Buffer came with caution that no, not all effective field theories can be consistent with quantum gravity. So he called the space of effective field theories inconsistent with quantum gravity Swampland. And Swampland conjectures are proposed criteria for rejecting effective field theory in the Swampland. So this is like a top-down constraint on the bottom-up effective field theory approach. And it's a little bit against the effective field theory philosophy of sampling. So the questions like that of string theory. So usually effective field theory thinks you don't really need to know so much about high energy theory. But the Swampland conjecture claim that they can actually secretly constrain the effective field theory at low energy. Well, actually that's what they want to do. So this is the space of effective field theories. So if you distinguish the effective field theories with different parameter values, then the space is continuous, and so each point in the C space represents one effective field theory. But so Swampland conjecture will kill like the effective field theories in this region. It's proposing it's not consistent with quantum gravity. And then there are several conjectures so far proposed. So this conjecture will kill this region, and this conjecture will kill this region, and we end up with very tiny consistent theory. That's the idea. So let me look at one example of Swampland conjectures. So one is distance conjecture. So this distance refers to the distance in scalar field space. So as scalar field go close to Planck scale, cover of light appears with some energy scale which decreases exponentially with phi, some order 1 constant. And this happens, so cover of light space is states parameterized by integers. So vector oscillation is quite common. So this means the new particles are coming into the effective theory. That means original field theory breaks moves down. And the more defined version of this one, the stricter version of this one is emergent string conjecture. So this conjecture proposes that this tower is either a Karuza-Cram Morse coming from the external momentum or fundamental string oscillation. It has integer oscillations doubled by integer. Another conjecture is weak gravity conjecture. This basically proposes that the gravity is the weakest force in nature. So when compared with gauge force, so charge must be bigger than the mass in Planck unit. So that is a proposal, and this makes effective field theory with small gauge coupling difficult. And if you consider Dirac magnetic monopoles and magnetic force, it will get this condition for the UV cutoff scale. And this also makes small e hard. If you make e small, the cutoff of your theory is becoming down and down. Your applicability is more and more restricted. Then there's a proposal that this weak gravity conjecture and the sun conjecture is connected. So if this UV cutoff goes down as you take E small, so it is identified with the sun conjecture, tower of light states appears. Okay, so then, okay, so this is a little bit critical view on swampland conjecture, and this is my personal view and also very qualitative view. But what I want to say is there are many swampland conjectures, and their plausibility and usefulness differ. For example, yeah, we have had this Rosita swampland conjecture or trans-Planckian censorship conjecture. These constrain effective field theory very strongly. But in my personal opinion, the theoretical basis that this comes from string theory is quite weak. So plausibility is actually quite low. On the other hand, distance conjecture and weak gravity conjecture, it's quite plausible. String theory has a lot of examples of these. However, what they are constraining may not be effective field theories, but something else. So the situation is like that. So originally, swampland conjecture tried to constrain this, but some of them only constrain the energy scale just below the string theory. Or something constraining effective field theory actually may not come from string theory. That is, I think, what they actually end up with at the moment. But people are trying to make some swampland conjecture more plausible. And the method is to try to find more and more examples in string theory vacua. You cannot prove by this way, but it becomes more and more convincing. Or also, zero, okay. So black hole is always a good testing ground for quantum gravity. You do some sort of experiments and see whether it's reasonable. Okay. Okay. So then, I have some work. So another question you can ask is if you have effective field theory which is constrained by swampland conjecture, whether this constraint will propagate into the lower energy to constrain. And to make long story short, so its situation is like this, and in this case, it turned out that so if this theory respect weak gravity conjecture, this theory also respect weak gravity conjecture. That's what we showed. And okay, I think I have. Okay, but this is the last slide, maybe. So then we also try to check weak gravity conjecture equals to distance conjecture. And so I skipped all this explanation, but so we propose extended proposal for string swampland conjecture, and that is crucial for describing some inflation model using effective field theory framework. And so summary, so I try to explain string theory to effective field theory via swampland proposal. And most of the conjectures still remain conjectures. And as I said, they might not constrain effective field theory contrary to the original purpose. And we made a case study for those constraints propagate to low energy or not. And in this study, we assumed the starting point, the swampland conjecture was expected, but it is interesting to check it in explicit string theory example. And I like to caution that so this is my views and may not be shared with many of my colleagues, but I'm trying to claim that I am correct. Okay, thank you.
For a couple of questions. Yeah.
So I have a very naive question about, you showed this picture about that there is several EFTs, and then comes the Planck scale. Then you said that at that scale EFT won't work, then we need quantum gravity. So what is the problem? I don't know that.
Okay. Yeah. So effective field theory we usually mean is in the flat space, or geometry is fixed, not dynamical.
Okay.
Making them dynamical is very difficult. That's one reason.
I see.
So actually, what I mean by quantum gravity here is UV complete quantum gravity. Actually, you can describe quantum gravity as effective field theory, but that has a limit in high energy.
So is it something to do with its renormalizability or something like that? So what?
Yeah, UV complete means renormalizability. Effective field theories are not renormalizable.
Yes,
Need
yes.
not be not renormalizable. And yeah, that makes some set the UV cutoff scale breakdown the perturbation.
Okay. Okay. Thanks.
Any other question? Okay, if not, let's thank Kazu again. And we move on to the next speaker, Deva Prasad Mehti.
Okay, so thank you, the organizers, for particularly specifically to Dhiraj for his tireless effort to make this conference happen, and of course invited me to speak on the topic that is related to very early universe cosmology. So this particular topic that I'll be speaking today is based on the work that we just finished, and we are going to submit it soon. But of course, those are the follow-up of a series of work that I have worked on with my several students, and out of them, Ayon already he has spoken, and Subhasis already has spoken. And today, Riyajul, I don't know whether he is here or not, but he will be speaking today. Okay, so before I start, let me give you the basic message that I wanted to convey through this talk is the following, that if we assume dark matters to be particle-like, then if there exists inflation in the standard model of cosmology, then this inflation will produce large-scale fluctuations, which is part of the title of my talk. And then that large-scale fluctuation is going to affect significantly the dark matter phenomenology. Or in other words, if I want to make it little more ambitious, then the statement that I want to convey is that the conventional phenomenological approach may not capture the complete picture of the dark matter physics if standard model cosmology includes inflation. So this is what the message that that I want to convey through this talk. Okay, so part of the reason that why the usual phenomenological approach to dark matter physics cannot capture the physics of dark matter is maybe one of the reasons could be this question that typically they don't ask is how does the present state of our universe arises. So this is the question that typically they don't ask. And with this slide, I am also taking this opportunity to say a few words. The present state of our universe certainly includes my campus as well, and this is the campus where we live and where we write papers. And there are several things. One thing that I should mention is these hills where Kamakha temple resides. So if you are interested in history as well as Indian culture, certainly you can visit. And of course, if you want to visit us, you can write to me, and then we will be happy to host you. Okay, coming back to the question, how does the present state of our universe arises? And what I want to emphasize is that inflation is the one which actually gives rise to this initial condition. So if inflation happens, and if inflation is part of the standard model cosmology, which is, we believe that the large number of cosmological observations already make us believe that yes, inflation could happen, then our inflation will have generically two phases. One is of course cold phase, and that is driven by inflation, and the another one is the hot phase, which is after that is coming, which is the standard Big Bang that we know. So of course I am not particularly interested in describing what is inflation and what is in hot phase. And the another point that I would like to mention, that all the standard model particle phenomenologies that do talk about physics of dark matter, they always begins with this assumption that there is a hot universe, and from there you start building up your model of standard model of dark matter. So in this talk, I will not be talking about inflation, I will not be talking about this hot Big Bang, but I will be talking about the phases, the phenomena that happens in between these two lines. Okay, and there are many questions that you can ask regarding this transition from inflation to hot Big Bang. Out of this, I will be mostly my concentration will be on this question: what role does inflation play on the dark matter physics, and then the follow-up questions related to the gravitational wave. Okay, so let me go a little more detail. So if inflation happens, then at the present time what we expect or what you see, of course, is just the background, and on top of that fluctuation. These are the one that you have been hearing over the last 3-4 days. So after the inflation, many things happen, and then finally what we observe is background and fluctuation. The backgrounds, what is the background, what are the fluctuations, I don't need to explain. And the main mechanism through which this transition happens is basically the quantum particle productions. So that is what the main mechanism by which you can obtain the inflation to the hot Big Bang at the present state of the universe. And such production mechanism will be driven by two classes of interaction. One is through non-gravitational, which is basically you construct your models of inflation coupled with all the standard model particle, and then you try to understand how this inflate and decay. And another one, which is the purely gravitational one, and which is universal in the sense that you cannot avoid having this. It is basically there, already there, even though you don't have any coupling of any field with the inflaton, but simply because gravity is there, so gravity will give you particle productions from the inflaton as well, moment you have time dependent background. I will be particularly focusing on this particular phenomena where particularly the dark matter physics, which will be produced by inflation purely through gravitational interaction. There is no interaction with the inflaton field. Okay, so what is inflationary particle production? It is extremely simple. It is the same as the one that you already know in the Swinger mechanism. So what it does, if you have a constant background electric field, then a virtual pair of electron positron will feel a force, and because of that force they will gain energy. And then if the energy of that electron or positron gain the energy which is compared to the energy of this rest mass energy of the particle within the Compton wavelength of the electron, then you can create a virtual pair to real pair. Basically, that is how the pair production happens in Swinger mechanism. So here exactly similar type of things happen in inflationary background. But for this case, you don't need to have the charged particle. It can happen also for any neutral pair as well. So if you have a neutral pair, virtual pair, then if you have background expansion which is exponentially expanding, then you can have a possibility that this virtual pair can gain a velocity which is close to velocity of light because of the expansion within the within the Compton wavelength of that particle. Then naturally that will give rise to real particle out of virtual particle. So this is what exactly happens in, but it is not, even though it is a simple minded picture, but if you want to do the real calculation, then what you have to do, you have to solve your the field equations in this inflationary background. Okay, so now what do you do? Let us assume that I have a scalar field which I assume to be a dark matter, massive dark matter. Then if you calculate the mode function of that scalar field in this background, typically you have this kind of equation where this is my time dependent frequency. Now you can see here the universe is expanding, so that is why the background is time dependent, and because of the time dependence your particle production typically will happen. Okay, the nice property of this inflationary background is that, as I said, that because there is a background time dependence, it is very difficult, you cannot define what is particle, because time because there is no time like killing vector, you cannot define the appropriate definition of the particle. So that is why you have to have something some limit where you can interpret your identify or define the particle. So a nice feature of this inflationary background on this particular background is that this frequency has a nice property. If you take very small wavelength in this limit, meaning if you go eta goes to negative infinity limit, then all these modes will be deep inside the horizon, and they will not see the overall curvature of the space time, and that how this particular feature can give you a handle that you can define a vacuum which is typically called adiabatic vacuum, where your frequency varies very slowly. That is called adiabatic vacuum, and you know this vacuum is known as this Barnes-Davis. So that means I can define a adiabatic vacuum for all those modes which are deep inside the horizon, and I can expand my field mode with respect to those modes which forms a complete Hilbert space. Similarly, same field can also be defined. There exists another adiabatic vacuum in the far future, where also this omega will vary very slowly, and you can define another adiabatic vacuum when those modes are deep inside the horizon, and there also I can define a vacuum where your fields this omega varies very slowly, and then you can define. So that means the same field can be expressed in terms of these modes in far past, and same field can be expanded in terms of these modes in the far future, where you can identify particle. You have the particle interpretation. And now you know this, if there is two vacuum here, the same field can be expanded into two different Hilbert space, then you can always relate these two Hilbert space by a Bogoliubov transformation. That is the standard technique that you do in quantum field theory and even quantum mechanics. And that is how precisely identify the particle number density. And that particle number density is actually related to this beta, and the standard notation. So if you have seen it before, then you can easily identify. And this alpha are basically the Bogoliubov coefficients, and they satisfy this SU11 relation. And then I identify beta to be my particle number density, co-moving number density. Remember that when I'm saying these are the particle, this is valid only when those modes are inside the horizon. This is very important. Okay, so now let us try to give you some typical form of this spectrum beta. But before that, let me just make a few comments. So if you take in inflationary background, if you consider massless fermion and vector boson, then because of this conformal invariance, those particles cannot be produced. So this is a typical property of conformal invariance. But of course, any massless scalar field or any massive fields can always be produced through this mechanism, this inflationary time dependent background. And of course, you will see here today another talk by Raghuvir, who will be talking about how to break this conformal invariance by taking into account the perturbation. You will see how there also you can produce the particle. Okay, so coming back to my beta. So typical form of the beta spectrum will look like this, a power law, and then there will be a complicated function of again E, which is a function of K, mass, and the energy scale in which you are talking about this. And you can see that this kind of form already you have seen, which is related to your structure form, the CMB fluctuations. Actually, this is exactly the same mechanism by which you consider the curvature fluctuations. Here also I do the same thing. I assume a scalar field, and then I do the expansion and try to figure out what is the spectrum corresponding to the scalar field, what you do usually for the inflator fluctuation. And I will be mostly focused on this infrared meanings which are greater than the scale which enters at the end of inflation. So that is why you call infrared. And all the modes that are within the Hubble horizon, inside the Hubble horizon, the later stage of the universe, we call it just ultraviolet. We will not talk about this, because typically what happens, all the modes which are inside the horizon has a suppression. Of course, this part of the scaling is not pretty generic, it depending on what kind of reheating mechanism you are talking. But since this is highly suppressed, I will be only focusing on the modes which are outside the horizon. Okay. Okay, so now if I assume this number density to be the number density of particles, dark matter particles, then how those dark matter will contribute to the phenomenology that we are talking about. Two possibilities. One is dark matter being completely dark, meaning that there is no interaction with anything. It is just purely dark matter, and only interaction that it has is the gravitational one. So that's why I call it completely dark. And another possibility that is there, which is related to the phenomenology that I was talking about, if this dark matter interacts with the standard model fermion, then how does this phenomenology of dark matter that usually people do alters because of these large scale modes. Okay, so this is dark matter being completely dark, meaning, so these modes are entering into the exiting the horizon, and these are the modes that I was talking about. These are all the modes which are essentially infrared modes, and they will enter subsequently in the subsequent evolution, and they will contribute to the total dark matter density that we have today. Okay, so what you do, you just calculate at the present time what is the total number density, and then you multiply their mass and you will get the dark matter abundance. And this is how, because it doesn't interact with anything except the gravitational interaction, so what we will have, it will just freely propagate and then contribute to the total dark matter content of the universe. And you can compute what would be the mass if I take into account solely those infrared modes. And this is how the mass versus delta relation appears. So you have only one parameter. Of course, I introduce this delta to be another parameter. I assume this delta typically, if you fix a particular model, then delta will be fixed. But for the time being, for our analysis, I just assume that delta to be arbitrary. Okay, so if you assume this vary this delta and mass, then typically, and this if the completely gravitational dark matter, meaning there is no interaction with the gravity, then these infrared modes are completely responsible for the present dark matter abundance. You can have a huge parameter space where these infrared modes will contribute to total dark matter that you have at the present time. Now I can go to next situation where my dark matter is no longer gravitational. All the dark matter phenomenology that people do, typically their starting point is this region, not in this region. So you have the thermal bath in this region, then from this thermal bath, you interact the dark matter with the standard model, and then you evolve. That is what usually they do. But now what you are doing, there is a dark matter infrared modes which will keep entering throughout this evolution. And that will contribute to this additional component, which is, I am saying, the infrared dark matter injection. So you have this traditional part which usually people talk about in the usual particle dark matter phenomenology, and we have this additional infrared injection coming from this long wavelength fluctuations. Okay, let me show you what is the parameter space. That is so typically we have two possibilities. One is called a freeze in and another is called freeze out, depending on how you produce from the thermal bath. Okay, so and freeze in is essentially meaning that dark matter interaction with the thermal bath is so weak that it will never become equilibrated with the dark matter. And freeze out means it is initially is equilibrated with the standard model, and gradually because of the expansion it will become out of equilibrium. So these are the two possible mechanisms by which you can produce dark matter from the thermal bath, and these are the two possibilities, and you get these two possibilities out of this single equation. Okay, so this is the freeze in, meaning when dark matter are produced from the thermal bath, but dark matter are never in thermal equilibrium. They have a finite value of interaction with the standard model, but they are never in thermal equilibrium with the bath because of very weak interactions. So they can only be produced from the standard model annihilation. And this is the parameter space that you have. And then if it is freeze out, meaning which is the standard one, we will find that the huge parameter space open up. This line is essentially the standard WIMP miracle that everybody knows. Meaning, if I talk about simple particle phenomenological approach, means there is no infrared modes, only standard model standard model of dark matter coming from the thermal bath. The only parameter space that exists in this simple model is this line. But now moment you include, remember this part contribution is completely universal, because this has to be there because it's just gravitationally produced. You cannot avoid having those. So if you include, then moment you include this, we have all this this huge region naturally opens up without any additional physics. Without any addition, I am not introducing any additional physics. It's just simply, if you have inflation, this is the contribution that you have. Okay, and now if I put it in the experimental parts, if you put all this data into freeze out and freeze in into the present context of taking into account all the existing constants, then this is the part which is still available. If we think in terms of freeze out, and this is the part completely available, which if you consider the freeze in. Okay, so there is a huge parameters but still available which has not been explored. And then at the final piece of final slide is that, so for every delta, this is the contribution. For every given delta, I have this parameter space, and that means, and because this delta is giving you a long wavelength fluctuation, that will contribute to the isocurvature. And we have also taken into account the isocurvature constants, and that is why I plotted the value which satisfies these isocurvature constants. And then because of the specific delta, and this will give you a long wavelength fluctuation, that can certainly give rise to non-trivial secondary gravitational waves. And this is the predictions of the gravitational wave for different deltas, which actually you can see that they are naturally passing through various upcoming experiments. Of course, I cannot go further up because that will naturally violate the standard delta n effective bound and R constants. Okay, so with this, let me finish, and this is my conclusion and some future directions. I think let me not read it out, and thanks for your attention.
Okay, one or two quick questions. Ah, Shriram.
I presume the chi field is coupled to the inflaton in some manner, and
No coupling here.
how was the chi field produced?
Yeah, that is precisely is because you have this time dependent background, and this time dependent background
Or
naturally.
it's just a chi field evolving in this background which is
Yes,
produced?
Yes.
Now, how do you know it's a dark matter particle? I don't know
No,
its
I just
pressure.
assume that as a dark matter. Yes, I just assume that. Okay, so the
I
question,
need to know the pressure density relation in order to claim that it is a collection of dark matter
yeah,
particles.
that is a good question. So that is the later part. So basically, what I'm saying that those dark matters. So these are the individual modes that will be produced during inflation, and they were never considered. But whatever people have considered in the usual phenomenology is whatever modes that is produced during this phase. So now what I'm doing, I'm just adding those modes that is coming from basically these modes. But those modes are already there before also in the usual phenomenological particle phenomenological model. Okay. I'm just saying there is an extra contribution coming from the inflation which were ignored before.
I agree
Yes.
the mechanism, but
Yes.
I think to claim that they are dark matter particles, we need to know the pressure.
Yes, we have to. Next thing is we have to calculate how this. So that is what
Just
my.
one brief question.
Yes, yes.
You got a k minus 3
K-
for beta k for k greater than ke somewhere.
K
So
minus-
can you, there, on the right hand,
Yes. Yes.
okay?
Yes.
Okay, but beta k square, k cubed is k minus 3. So beta
Yes.
k square is k minus 6.
Yes. Yes.
Okay, what kind of transition do you have?
So it is. Okay, I have taken this instantaneous transition. So from inflaton to directly radiation domination. If I include so if I include some other phase, then there will be a difference. Yes. In the spectrum. Yes. Yes, you have done that. Yeah, we have done that, and that can also actually give you successful reheating. If you look at our paper, it's called gravitational reheating. We have done that. Yes. 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 No, so because that is why this definition of adiabatic vacuum is important. So we can define this particle here, and we can define particle here, and because of this non-trivial time dependence, we interpret that as a particle is produced, and that produced, yes. Yes. Yes, yes, you can, that is why I am saying this is pretty universal. You can talk about any fields. I mean, all the standard model fields will also be produced, and that is what his question. If I produce all the standard model fields, whether that can give rise to some process. So we have actually studied that, and we found that if you produce Higgs can be produced, and that can actually contribute to the reheating. In fact, this simple gravitational production of Higgs can also give rise to reheating completely. We don't have to interact the inflaton field with the standard model. It just gravitational production is sufficient to reheat the universe.
Okay. We'll start again. So we move on to the next speaker. जो भी कुछ
Okay, can you hear me? Okay. So, good morning everyone. I'm glad to have this chance to present our work in front of you all. And today I'm going to talk about our observational constraints on early dark energy. And this work was done in collaboration with Lu at Shanghai University and Bomhoon at Sogang University and Tuhin at Nizar Bhubaneswar. So, just a quick introduction to cosmic birefringence and early dark energy, because these are important to what I'm going to talk about. And cosmic birefringence is basically the rotation of the plane of polarization of the CMB photons, and this leads to non-zero EB cross correlations in the CMB data, and this arises due to parity violation, and in the standard lambda CDM model we expect this cross correlations to be 0. Now, this has been detected with almost a 4 sigma significance from the W map and Planck maps. So, it is interesting to look at possible origins for this signal. Early dark energy was a model initially proposed to alleviate the Hubble tension. So, it says that basically there is some dark energy like component in the early universe before recombination, and that accelerates the expansion rate to increase the H0 that you infer from the early measurements such as CMB, to reconcile it with the H0 values that we get from late time measurements. And incidentally, it gives us a very nice bonus that in some dark energy models where the based on axion like fields, so that are modeled by a scalar field phi with this kind of a potential cos phi by f raised to n is a phenomenological parameter. Then the coupling of the axion like field of the dark energy field with the CMB photons through the electromagnetic tensor, this coupling can generate cosmic birefringence. And so it gives us a very exciting possibility that early dark energy might be able to explain both these phenomena with a single model. So, it might be able to, but does it really do that? And that's what we try to check. And I'll talk about the parameters. So, you have your standard 6 parameters from the lambda CDM model, and you have additional 4 parameters. So, you have FED, that is your fraction of early dark energy. GED is the coupling constant, the strength of the coupling that we just saw, and ZC is the critical redshift at which the field starts to oscillate, and after that it starts to decay very rapidly. It is required so that it does not affect the late time expansion history of the universe, because that is very well constrained by large scale structure. And theta I is the initial value of the field. So, we have these 4 parameters, additional parameters on top of your 6 standard lambda CDM parameters. And we are going to try and constrain this using the data. So, what is the data? So, we use the CMB data from Planck, and we use the BAO data, and we use the Schu's measurement of H0. So, these are available as direct packages in the Kobaya MCMC software package. And basically, so previously you can find some work by Eskild's group, Eskild and Komatsu, and what they do is they previously, before this detection of cosmic birefringence, they tried to fit the early dark energy model without the coupling, so without GED. So, that leaves you with 9 parameters to the CMB data, and they have best fit values for these 9 parameters, right. So, what they do is they take this data and they fix the 9 parameters to these best fits that they have obtained previously, and they fit the EB data with this coupling constant GED, right? And this way they obtain a fit to the EB data, and that is represented by the green line in this figure. This green line that you can see, that is their fit, and the black points with error bars are basically the data. So this is your EB power spectrum, and as you can see clearly, it does not really agree with the data points. So they claim that the shape of the EB power spectrum as predicted by this early dark energy model, it is not consistent with the cosmic birefringence measurements, right? So while we were trying to reproduce this data, we found that the shape of this EB signal, that actually depends on the background cosmological parameters, and so it is important that you vary all these cosmological parameters also, not just keep 9 parameters fixed and change the coupling constant, but you have to fix the entire 10 parameter set, and you have to find the best fit that way. So that is what we do, and our result is represented by the yellow line. So this line represents our result, and it seems to provide a reasonable fit to the observations. Now we should look at the size of these error bars, and at this stage, because we lack a very precise measurements of this signal, it's a bit of a chalega measurement. So we are not in a position to actually say that early dark energy is the suitable explanation for this model, but what we can say is that it is definitely consistent with what is the current measurement, and it is not ruled out as people previously claimed that it is ruled out. This cannot be explained by early dark energy. So that is not the case, and these are 72 data points. So our chi-square, that is the yellow line, that is 68, and the previous group, they found chi-square of 103 for their best fit. So we have a much better fit to the data by relaxing the assumption that the shape of the power spectrum does not depend on the cosmological parameters, and now we are finding it is consistent with the data. And this is the best fit parameters that we obtain. So this second column represents the best fits, and the third column are the marginalized values, and I'll leave you to see this for a minute. Okay. So now there's one more aspect to this. So there is something called miscalibration angle. So if your detector is not calibrated properly, then that can record a rotation of the plane of polarization, and that can also produce cross correlation between the E and B modes, and that can give you an EB signal, right? So the question is, can we actually separate the instrument miscalibration from what is a cosmic signal of birefringence, right? So we did a quick check, and we found, so this is the EB power spectrum and the blue line, right? So your instrument miscalibration is this angle alpha, and if you can consider a constant rotation angle beta. In our case, for the early dark energy model that we consider, the rotation angle is evolves with time, evolves with cosmic time, and it is not a constant. But if we consider a constant angle, constant rotation angle, then that is represented by the blue line here. And for our model, not our model, for the model that we consider, it is the power spectrum is represented by this yellow line. And you can notice that there are subtle differences in the shape of the power spectrum that you get from a constant rotation angle and from this early dark energy model. And with these error bars, we can definitely we are not in a position to disentangle the two as of now. But maybe if we have more precise measurements in the future, then we can detect these differences in shape, and then we might be able to separate the miscalibration angle from the cosmic birefringence signal, and we might be able to really tell whether this model is a good fit to the data or not. So I will leave you with the summary.
Thanks, Obi. You finished ahead of time. So we have time for questions. Okay. Srinath first.
Hi, nice talk. So Tuhin was mentioning about the EB signal, and he also mentioned that dust, effect of dust or difference in dust modeling can make them all vanish. So,
Right, right. So, so you're asking whether that can contaminate the signal.
so have you explored the effect of?
So that is
And,
a concern. So what about the dust signal, right?
Okay.
So this dust is more foreground, right? So it is relatively very close. It is a relatively very close source to us than compared to the CMB. So we are saying that this rotation birefringence is coming through the coupling of the CMB photons with the scalar field. So that is evolving from last scattering towards today, us. Relatively, we can say that that is a very short time. So we can treat that effectively as a constant. So when they make the data, they consider it as a constant.
Okay, thank you.
So that is something to be probed, but maybe in the future.
Can you go back to the best fit values? So there's a paper out today, if you've seen it, where they combine ACT and SPT and they come up with bounds on F early dark energy, and they seem to exclude something till 0.08, whereas your model seems to prefer some value that's relatively high.
Which parameter?
ACT and SPT and Planck.
Right. Which are you talking about? FED?
FED, yeah.
They get
Something like 0.08 is their best.
right. So if you look at if you look in the literature, then people have assumed different set of background parameter values. And like I pointed out, that you can start with a different set of parameter values, and you'll get a completely different bounds. So I have not read this paper. I don't know what are the assumptions that go into it.
Do you think they may be neglecting GED or something like that?
I'll have to read and check. I don't know, because previously there is another paper by Vivian, Pauline, Tanvi Karwal. They take a different set of parameter values, and they get a completely different bound. And if you take those best fits and you fit only GED, it will still provide a good fit to the data. But you take this set of 9 best fit parameters and it does not fit the data. So it depends heavily on your assumptions. So basically we are saying that we should relax these assumptions and we should do a full fit instead of.
Okay, thanks.
Hi. So it is related to Orko's question. So this is the Vivian, Pune, Tanvi and Mark's model, right?
Yeah.
So they showed that their model parameters change when you add H0 and just
Yes.
use the Planck.
Yes.
So when you have this, what are the data sets that were used in this one? EB, right? EB is there. So if you use EB, the ZC, ZC value is very, that prior, okay? So that is very highly localized, I believe. If you allow the prior to go for the entire cosmic time,
There
you
is
do not
something
get
called a
any
shooting
evidence
process.
or
Yeah,
something like that. So you have to put a tight prior.
Yes,
So my question is that whether this tight prior that you are imposing includes the main model that initially came to solve the Hubble tension.
Yes. So I think.
Is it consistent and things like, because what I'm asking is that whether the best fit values change when you add EB, because the first one was not with the EB.
So I have not shown that plot. So
Okay.
they themselves have 9 parameters. No, they did not consider EB.
Yes.
So you
My
can
question is-
take those 9 parameters and you
Yeah.
can fit this coupling constant, and you can find that it still provides a good fit to the data.
Yeah, H0 is still increasing, but this does not include the H0 prior, right?
We
You
have-
are using the H0 prior here?
No.
Oh, SUS is
So
there.
SUS data is there. Yeah.
Okay, then there is one thing that if you use SUS prior, it is going to drag it anyway.
Right.
So without the SUS prior, TTT, EE, and I think even with the EB, you will not get any signal on the early dark energy.
Sorry.
Without the SUS prior, you will not get any preference only from Planck on the early dark energy.
So I think they have done, no, Vivian, Pauline, and
Yeah, that
and
was-
they,
yeah,
they get the tension close to like maybe less than 2 sigma.
No, only when you add SUS prior. If you do not use SUS prior, the FED is completely consistent with 0. Actually, the marginalized confidence contour is actually picking at 0.
So we have
I
done
will
without SUS
talk to you
also.
later on this.
Sure.
I had the same question on this set of parameters that you had shown. Your NS seem to be very large, right? I mean, with the data set you are fitting, but your NS, will it fit the CMB data?
Yes, it does.
But then you are messing up with the CMB spectra itself, right? Oh.
The problem is that here, if you do not use H0, NS stays the same and FED stays as that from line. You have to include H0 to do this thing. Then there were later paper came with ACD and all that goes where they are.
Okay.
So just a clarification on the previous slide, just a clarification. The table which I think, so what's the difference between best fit and marginalized? Usually best fit is also obtained by marginalizing over other parameters. So maybe I missed this. So what is difference between the second and third column?
So you can see that we don't have very well behaved posteriors. We have a lot of degeneracies. And for example, even so you integrate over all the other parameters.
So the best fit is from a frequentist analysis?
In some sense, you could think of.
So are you using profile likelihood?
No. It's the best chi-square.
You do a markup chain multiplier or nested sampling. You get a lot of points, okay? So you do whatever you want, but from there will be one point that actually gives you the lowest chi-square. Right? That is the best fit point. And those points, the marginalized ones, are from individual, after marginalizing each parameter, the individual mean values. So if you take the individual mean values and you try to plot the CMB spectrum, it can be way off from the CMB spectrum. So those are the mean values for each parameter. But the best fits are the set of parameters, the theta I of the best fit. That gives you the minimum chi-square. But the marginalized one will not give you the minimum chi-square. So,
Hi, thank you for the nice talk. Maybe you already said it and I missed it. What was the beta parameter in the miscalibration?
Oh, this one?
Yes.
So beta is the rotation angle due to cosmic birefringence. So you can consider a constant rotation
So
angle.
alpha is the miscalibration.
Yeah.
Okay. So
or a time evolving one like we consider.
right. Yeah. And did you here in the miscalibration did you consider any frequency dependence or it's just constant?
They found that it did not have a frequency dependence. So Eskelt and Komatsu's group they extracted the data from Planck maps and they found that it did not have a frequency dependence. There was no signal for a frequency dependence.
Okay. Thanks.
Okay, let's thank Joby again. And we move on to the next speaker.
Good morning everyone, I am Riazul, I am a postdoctoral fellow at ISI Kolkata and I will talk about the primordial black holes, a window into dark matter and gravitational sources. And this talk will be based on these 5 references and those talks has been done in collaboration with this paper. So this is my outline of my talk. So first of all I try to motivate that why we considering the primordial black hole at the very early universe and what is motivating by considering this considering the primordial black hole. Then I move to my goal by considering the several gravitational and the dark matter sources associated with these black holes. Like for the stable black holes, we knew that the stable black holes can be treated as a dark matter, and I will show that in which parameter space of the black hole mass it can be treated as a dark matter. And then I look into the evaporating black holes, where typically I consider the black hole mass less than 10 to the power 9 gram. In that case, it's ultralight and it evaporates before BBN. In that case, I am talking about that what will be the dark matter parameter space associated with it. And finally, I move into the gravitational signatures associated with this primordial black hole, and talk about 4 different sources. One is associated with the formation. We know that if the black hole form from the inflationary origin, if we have USR kind of model, or we have a bump or dip-like features in the potential, it generally leads to a enhancement in the curvature perturbation, and that can form primordial black holes. So that can also leads to a induced gravitational wave. I will talk about that. And then the isocurvature perturbation, because these inhomogeneities in the PBH number density, that can lead to the isocurvature perturbations, and that will also lead another induced gravitational source. Then the adiabatic one, which is associated with the inflationary perturbation, even for the scale invariant inflationary power spectrum, that what happens if you have a PBH domination era, so density perturbation will grow, your burden potential is constant. In that case, if there is a sudden transition from primordial black hole to radiation domination, that also leads to this kind of induced gravitational wave. And finally, the evaporation induced emission. This is simply, you can say, that the graviton production from the evaporating black holes. And finally, I talk about how the memory burden effect and the non-standard cosmology will impact on the production of the dark matter and gravitational wave. So finally, why primordial black holes? I already talked about that we didn't know much about the very early universe, the before BBN physics. We only have observations of CMB, and we know the relics from the BBN. But if we consider the black hole is one of the candidates there and form after inflation, then have several sources, gravitational wave and dark matter associated with it, and that can give rise some detectability of this very early universe. That is one of the motivation. And another is that recently that the detection of these gravitational wave by LIGO also hints the potential presence of this primordial black hole. So now go to the PBH formation during early universe. There are several possibilities. One is associated with the inflation, and the other one there is a preheating, but in the all case they all are fine-tuned process, because during preheating also the instability can go the density perturbation and form structure can form, and the primordial black hole can also form, but that will depend that the collapse time scale and also the preheating time scale. And the other of collapse of domain soil and the other from different origin, the black holes can form. And if you consider once the primordial black hole can form, so it will start to evaporate it, and the evaporation is not a pure black body, there is a deviation from the black body, so you need to calculate the gray body factor. So this is the energy spectrum of the emitting particle, of the massless particle, and this is the different spin. I have shown that what will be the flux of the emitting particle. So once we calculate the flux of the emitting particle, then what we need to do, we need to calculate the total evaporation function associated with those flux. We have to integrate out of the energy scale and calculate the total flux. And this evaporation function, it depends on what kind of particle we are interested to produce. If we consider only the production of the standard model particles and the dark matter, so typically the degrees of freedom should be that around the 108. And then we need to compute the mass dissipation rate of this black hole, and finally we go to the phenomenology of that. So one of the typical phenomenology we can consider that will be the production of the dark matter, but let consider what are the restrictions on the PBH parameters. If it is ultralight and evaporating one, not stable till today, so then there are several constraints on the primordial black hole. So one is coming from the BBN. So you need to evaporate before BBN, otherwise there will be other restrictions on that. And the horizon size, if we consider the collapse of the horizon, so the typical size of the horizon is around 1 gram at the end of the inflation, considering the maximum energy scale of the inflation, obviously. So then we can say that the D will be the allowed range for the ultralight black hole, which will do phenomenology. And other than that, there is a restriction on the beta. As I already mentioned, if there is a PBH domination, there will be induced gravitational wave associated with the isocurvature and adiabatic fluctuations. For the isocurvature one, this is the typical restriction on the beta parameter, because otherwise it will overshoot the delta and effective constraint. And for that, for this equation, we consider the PBH form in the radiation dominated universe. Now go to the constraints on the primordial black hole. So let's say consider the primordial black holes as a dark matter. If the primordial black hole as a dark matter, the only window we have is between 10 to the 17 to 10 to the power 21 gram. And obviously consider the constants, obviously consider the monochromatic mass function. If we consider the extended one, then definitely that will, that restriction will shift. And the reheating and the dark matter parameter space from PBH evaporation. So it's ultralight, considering the ultralight black hole, so one of the natural scenario, the production of the standard model particles. and in that case it can reheat the universe, even it will not dominate. So two different scenarios is there. These correspond to the case where PBH is not dominating, this is the PBH beta independent scenario. So what is the beta? Beta is the energy fraction at the point of formation, that is the beta. So rho PBH over the rho total at the point of formation, it is defined in that way. And now so it can reheat the universe, and also the dark matter particle can produce, other relics can also produce. So here we just shown this, how the dark matter parameter space, correct relic dark matter parameter space as a function of the formation mass. So now move to the gravitational wave signature. So first signature I talk about the associated with formation. So if we consider particular formation mechanism associated with the inflation, so you can say it like the USR kind of model is which leads to enhancement in the curvature perturbation, and if the enhancement is strong enough, if above 10 to the power minus 3 close to unity, then what happens? When this overdense region is re-entry during the later stage, during this radiation domination of the reheating, then it can collapse depending on some critical value, density contrast value, and it can form primordial black holes. So once this primordial black hole can form, and this is the this is the typical scale we are interested in. It's small scales, and the amplitude should be very high. As I already mentioned, the amplitude should be close to unity. And for just a schematic picture of this gravitational wave signal, I just considered the power, the broken power law kind of power spectrum, which has k to the power 4 behavior ascending, and the descending part I wrote in here n0, but actually it's 2 you have considered for this figure, minus 2. And now this is the density contrast relation, and which is depends on the background. But generally speaking, this is not exactly correct, because the density contrast is also depends on the profile of the curvature perturbation. But for simplicity, I consider that okay, it only depends on the background. But in the general way, depend both background and the profile of the curvature perturbation. Now we can calculate what is the fraction of the dark matter contributed PBH today, and then this is the induced gravitational signal. So here what happened, that the tensor perturbation at the second order, it is sourced by the scalar perturbation at the first order, and this is that kind of inflationary model we are taking, which leads to the PBH formation. Okay, so these are the another signature that the isocurvature and the adiabatic one. This is the adiabatic, this is the isocurvature one. So there is a inhomogeneities in the PBH distribution, so that can generate the isocurvature perturbations. And the another situation, that simply the adiabatic inflationary perturbation that can also grow during a matter dominated era. And we know the burden potential is constant during this matter domination, and if there is a sudden transition, it will not get enough time to decay. So there is an enhancement in the induced gravitational wave. So these two type of sources is associated with the PBH dominated scenario for ultralight black holes. So now let's say another source, this is the Hawking evaporation case. So direct graviton production from PBH evaporation. So this you can see this is dependent on the W in which background primordial black hole form, and that we can calculate from the flux of the graviton flux emitting from the black hole, and this is the typical dependency, and this is the high frequency gravitational wave. So now I just make a comment that if have some quantum correction on the Hawking evaporation, because the semi-classical assumption is not quite correct, because the quantum back reaction will trigger, and that will reduce the dissipation rate. And in that case, what happens, even the small mass black hole can be stable. And this dissipation rate is modified by 1 over s to the power k, whatever the entropy contained in the black hole. So now these are the modified parameter space. If we consider this Maury-Burton effect, which is stable even the ultralight one, so we can see that even for very low mass black hole can be stable today for higher order discorrections. And these are the for a reference plot for k is equal to 2, we can say this can be the FPBH equals to 1 line. FPBH can be 1 in that mass range. And other constants will be there, like the galactic gamma rays and the extragalactic gamma rays will be there. Now here we compare the signatures from, I think in the Wednesday also, Rajiv also told about this kind of signature, that how the reheating and the memory burden effect mimics each other. So what happened, actually this kind of induced gravitational wave is typically depends on the duration of that PBH domination. And if we have a lower, higher value of equation of state where the primordial black hole is forming, then in that case it elongates the PBH dominated era for a particular values of beta. And on the other hand, memory burden effect also elongate this PBH domination. So this Basically, both this non-standard cosmology and the memory burden effect regulates the duration of the PBH domination, and as a result we are getting a higher amplitude for a higher value of omega, and as well as when we introduce the memory burden parameter. For the second peak, the isocurvature one, if we calculate a degeneracy parameter between reheating equation state memory burden parameter, this will be the parameter space, but that degeneracy can be break if we consider both peak. If both peak can be detected, then the first peak with associated with the adiabatic one can be distinguish the signature of the reheating and the memory burden effect. And then this is the final plot where I show the gravitational wave from in-flight on to the primordial black holes. Here only I removed the adiabatic one, but this is the this typically the source for the isocurvature, and this is the in-flight on scattering source I have also considered, and these are the high frequency one which is the graviton production. And the solid dashed lines are for memory burden. And for the memory burden for the high frequency, we are getting the two peaks, and this is typically because the memory burden effect trigger after when the mass of the black hole becomes half of the initial mass. That's why we are getting two peaks in the high frequency gravitational wave. So this gives a distinct signature in there. So this is the complete picture from in-flight on to the primordial black hole scenarios. So finally I conclude my talk. So I am trying to motivate that PBH can be a good source of dark matter, and as well as the gravitational wave, the induced one and all the high frequency gravitational wave, and also that there are the effect of the memory burden and the non-standard cosmology on this gravitational wave also. Thank you for listening.
Okay, questions?
So, where will the, okay, let me track back. The constraints on beta, they should depend on the form of the power spectrum, right? You seem to arrive at constraints independent of the form of spectrum that one has, primordial spectrum.
Because in that case we didn't consider any formation mechanism, so beta is a free parameter. Anyway, you can connect it with your power spectrum and the amplitude of this power spectrum and so on, but here beta is a free parameter. So independent of what kind of formation mechanism we are taking.
I understand. Okay, and the memory burden, I mean, it's including adding so much uncertainty to all your predictions now, right?
Yes.
I mean, there is nothing well understood about the memory burden itself. There seems
nothing
to be
well understood. It's still independent.
sufficient freedom there. Am I right?
Yeah, yes.
Okay, all right.
Yeah, definitely, yes. So I think it's misleading to just show this. Because these kind, yeah, definitely, because these kind of curves we considering only the instrumental noise.
Astrophysical gravitational wave. In the millihertz regime, you get it from white holes.
I didn't consider any uncertainties from the astrophysical, because whole region. Okay. You know which frequency range that will lie? Which frequency range that will lie?
Around millihertz, they have white dwarf backgrounds from galactic white dwarf lines. Nanohertz, no,
but in the millihertz, in the millihertz range, that will lie. Okay. Yes. Because for the sensitivity curve, we only consider the instrumental noise. For the sensitivity curve, only the instrumental noise is taken care. Yeah, that is right.
Okay, Devika.
Hi, thank you for the very interesting talk. I have a question about this double peak structure. So what are these frequency profiles like? How do they rise and fall?
Behavior of the peak?
Yeah. I mean both of the peaks. What is the frequency profile like? Like f to the power what?
f to the
Index.
power, I think, as I remember, 11 by 3 plus some W dependency would be there.
Okay.
And if their memory burden parameter is there, then there will be effect from this memory burden.
So
This peak, the spectral shape is also depends on which background is forming and as well as what kind of evaporation process we are taking about.
okay, so from the shape of this peaks, you can tell something about about what exactly?
The distinct signature of the reheating or the memory burden, yes. There is a degeneracy between memory burden and reheating,
Yeah.
which we can take considering both peaks. Yes, for without memory burden, without non-standard cosmology, the spectral shape will be different.
Okay, so you can differentiate
yes,
between.
yes,
okay,
sure.
okay, thanks.
Okay, so let's thank Riyajul again. And we move to the next speaker, Shibendu Gupta.
Hello? Okay, it's okay. You can hear me? Okay. So, hi everyone. In this talk, I will discuss about one of our recent work based on Celeron as a dark matter candidate. So, as we all know that there is no universally accepted origin for the explanation for the origin of cooled dark matter, and there have been extensive experimental search for particle dark matter candidates, and still now there is no significant and conclusive evidence for such candidates. So, this suggests that if there is an interaction of dark matter with the standard model, then it is very feeble, and the natural question arises in this context is that is there any mechanism within the existing setup so that we can explain the observed dark matter relic density. Now, we know that all particles interact with each other through gravity. So, if dark matter comes from the gravitational sector, then there will be a natural suppression of interaction with the standard model particles, and this will naturally lead to the non-observation of these signals in the direct and indirect experiments. So, in this work we have considered the R square gravity, and we want to see if this R square gravity can account for the origin of dark matter. Okay. I will start with this action. So, in this action we can see, so this is the Einstein-Hilbert term, and we have incorporated the R square correction, and this term has been extensively used in the context of inflation, which was originally introduced by Starobinsky, but in this work we have used this term to see if this can account for the origin of dark matter, and this is the Lagrangian corresponding to the Higgs field, and we have also incorporated a non-minimal coupling of the Higgs field with curvature. These kinds of terms are very well studied in the context of Higgs inflation. Okay. So, now if we do a conformal transformation of this action, we can go over to the Einstein frame, and in the conformal factor is given by this, where this phi field, which is the scalar degree of freedom of R square gravity, is known as the Celeron field, and after choosing an unique canonical unitary gauge, we will get this effective potential for this phi field in the Einstein frame. As we can see, there is an explicit interaction of the Higgs field and the phi field in the Einstein frame, besides that coming from the non-minimal coupling. Now, having this potential, we can write down the evolution equation for the scaleron, and this is the evolution equation where we have assumed that this phi field is very, very smaller than the Planck scale. So, this is now the evolution equation where this phi 0 h, so this is the minima of the effective potential. As we can see, this minima depends on the Higgs field. So, as the Higgs field, if the Higgs field has dynamics, then this minima will also shift. Now, let us consider a very specific condition, which is this condition. If this condition is satisfied, then this phi naught h is 0. So, the scalar field is effectively free, and we have this equation. Now, to produce dark matter in this context, we have to rely on the standard misalignment mechanism, which happens due to Hubble friction. So, when at a very early times when the Hubble friction is very large, phi is misaligned to some initial value, and then oscillation starts when the Hubble becomes comparable to the mass of the scalar field. And in that case, we can explain the observed relic density, and the relic density can be obtained using this formula for such a misalignment mechanism, and this comes out to be this one. So, now here the relic density depends on the non-minimal coupling and the initial misalignment of phi also, and by this relation the mass also depends on the non-minimal coupling xi. So, if we fix xi and then demand that this relic density should match the observed relic density, then we will have bounds on this phi initial. So, this is the plot of the parameter space. So, in this axis we have the mass of the scalar field, and in this axis we have the initial misalignment. Both depends on the value of xi. So, xi is actually the independent parameter in this plot, and this is the line for the observed relic density. So, this part is excluded by LHC constraint, and this part are excluded by gamma ray. So, these are very preliminary results that I want to mention. Now, so as you can see that if we assume that the scalaron constitutes whole of the dark matter, then still a range of mass is allowed, where the phi initial is at around 10 to the power 10 giga electron volt, and the mass like keV to MeV masses are still allowed. Okay, so this is for the very specific condition. Now, we will consider the case when we do not assume any condition. So, in that case the Higgs field has a dynamics, and the minima of the scalaron field is not equal to 0. So, in that case we can find the crossover temperature where the electroic crossover of the Higgs field happens. For that we have to incorporate the thermal correction to the Higgs potential, and the crossover temperature comes out to be 154 giga electron volt. Okay. Now, before the electroic crossover, Higgs was sitting at h equal to 0, and therefore, the initial value of the scalaron is given by this. So, here we have a natural kind of misalignment without any fine tuning. So, this is very novel in this context. So, the dynamics of the Higgs field will now determine the misalignment and will determine the shift of this phi field. Now, after the electroic crossover, this is how the Higgs field will evolve, and this will also lead to a dynamics of the scalar field. The minima of the scalar field will evolve using this equation, and as h attains its vacuum expectation value v, the minima will be 0, and the scalar field will oscillate around this minima at phi equal to 0. Okay. So, now we can write, if we write this equation in terms of these dimensionless variables, we will have this equation for the scalaron evolution, and we need to solve this equation to see if the scalaron can account for the cold dark matter. Now, using this entropy conservation and assuming a radiation dominated universe, we have obtained this solution for the scalaron field or the dimensionless field, and this is actually an oscillatory part, and this is the mean shift or the average shift of the minima field of the minima of the scalar field. Now, using this approximate solution, one can show that that if we define this quantity chi, which is given by this, then this quantity I, which is a cube E, this E can be thought of an energy density of this chi field. This actually remains constant, and as h attains its wave value, so this becomes 1. So, the chi field becomes the phi tilde field at late times. So, E is the effective energy of phi tilde field at late times. So, and now this quantity E always scales as matter, because we always have a 1 by a cube scaling. So, we can find the scalar energy density at late times if we multiply this E at late times by the initial phi square, and the relic density comes out to be this, which is a function of m. If we demand the relic density to be 0.12, then the mass of the scalaron is fixed at of the order of 10 to the power minus 3 electron volt. So, the mass comes out to be very small in this case. Now, now we have used this mass value for the numerical computation, where we have incorporated the variation of G star and the full system, no approximation. So this is the evolution of the scalar-on field, as you can see. So this dashed line is the minima shift of the scalar-on field, and on top of that there are small oscillations. And this is the plot of the energy density of the scalar-on field. This dashed line actually gives radiation-like scaling, and this is the quantity phi I square E, which scales as matter. As you can see, initially the scalar-on field behaves as radiation, and after that there is a transition, and then it follows this quantity which scales as matter. So there is a radiation to matter like transition at some epoch, which means that with this mass, this field can explain the origin of cold dark matter. Okay, now these results can be readily extended to the case. All these cases for xi equal to 0, which is simplest case. All the results can be extended to the case where the non-minimal coupling is not equal to 0. And in this case, if we again demand the relic density to be 0.12, the mass of the field comes out to be this. This is a transcendental equation. However, you can find the root of this, and as we can see, the mass does not change for the allowed range of xi. So even with the non-minimal coupling, the mass comes out to be of the order of 10 to the power minus 3 electron volt, and there is a transition from radiation to matter-like behavior far before matter radiation equality, and no violation of BBN constraint. Okay, so I will summarize and conclude. What is the aim of this work? The aim of this work is to explore the potential of R square gravity in explaining the origin of cold dark matter in the presence of a non-minimal Higgs coupling. And for that we have the mechanism is that the scalar degree of freedom of R square gravity is producing the cold dark matter by two different misalignment mechanisms. In the first one, a very specific condition is needed, and we need to misalign through Hubble friction, because effectively there is no interaction, and for that a range of mass and initial misaligned values are allowed for matching the relic density. However, in this case where there is no specific condition, the misalignment is due to the explicit coupling between scalar-on and Higgs, which is very novel because we do not need any fine-tuned condition. This is misalignment to coupling, and then there is a transition from radiation to CDM-like behavior, but the mass comes out to be very small. So these are all the results that I wanted to discuss, and these are the references which I have used to prepare my talk. And I want to thank ANRF for the financial support, and thank you for your attention.
Okay, so we have time for a couple of questions.
I missed the first few minutes, so apologies if this was covered there. So you showed somewhere gamma rays, okay, limits from gamma rays, but I thought this couples only to gravity, the dark matter candidate. So how are gamma ray observations relevant? So is it, does it annihilate to gamma rays in the same way as standard WIMPs, or?
Yeah, it can annihilate to gamma rays. We have considered only the interaction with Higgs in this work.
Okay.
But it can in principle be coupled to all the standard model particles. Okay. But the dominating contribution.
Okay, so basically as far as coupling or annihilation standard model particle is the same as standard WIMP, right?
Yes.
Okay.
So there can be a coupling like phi if mu. So it's basically kind of a decaying dark matter scenario, but that is very feeble, so that it becomes a dark matter. But from there, that gamma ray bound comes.
Okay, I don't see any more hands. So let's thank Shibendu and all the speakers of the morning, and we break for coffee.
Okay, welcome back everyone. So we are now going to start the second session of the final day of the conference, and our first speaker in the session is Anirban Das.
Thank you.
thank you. Yeah, we have time for questions.
So, you said that for cosmological observables, neutrinos and dark radiation are interchangeable except at late times, right? Like, unless you're assuming a mass for dark radiation. CMB, it's fine, yeah. So then you should be, if you add late time data more and more precise, you should be able to constrain this model better and so on.
Yeah, hi everyone, thanks for the nice talk. I'm curious, I mean, you're basically doing a self-interaction by using nu goes to phi goes to chi. So you'll again have all these high energy astrophysics and the laboratory constraints, right? From the neutron you will emit a phi, and the pion decay, the monochromatic muon will change immediately, depending on the chi mass.
Hi. So the 2506 paper, the one that you showed, there is a peak and it flattens out at Z effective at 0, right? So this one, since you are using DAISY ER1, I'm interested in seeing the omega matter and whether it has anything to do with the bimodality. Whether omega matter also has two peaks at one at 0.31 and one at 0.27 or 26. Because I don't see anything with the neutrino mass, for example. It is completely uncorrelated. Okay, sure.
So my question is regarding this model where there is coupling between phi and two nus. So in that case, decay of phi can introduce more neutrinos into the system. So how do you take into account that, or too much suppressed coupling? So in this diagram, so this phi can go to two neutrinos. So then, yes. Okay.
So a very naive question. So when you are considering this kind of coupling, are you considering neutrino mass? Okay. And these also have supernova cooling bounds also, right? So this neutrino to dark radiation from supernova cooling? Thanks a lot.
Okay, it's time to move on. So let's thank Anirban again and move to the next talk. So our next speaker is Raghuvir Garani. Thank you. We have time for a few questions. Start with Sriram.
Raghu, you produce particles, massive particles possibly, but why do you call them dark matter? Will they have zero pressure? How do you know that? No, but you don't have a feel for what is the pressure involved and so on. This is produced from a quantum vacuum. So you have calculated some number density, that's all. Yes, but you still don't know the total pressure. But don't I need that to be vanishing in order to claim that it is cold dark matter? A quantum field, its pressure and energy density will depend strongly on the background evolution. But it is you are generating from a quantum vacuum. Okay, we'll talk.
Yeah.
Okay, so there is this another process where two inflaton goes to dark matter via graviton exchange. So, is that the subdominant compared to the one that you have calculated? Yes. Yes, that I agree. Yes. Mm-hmm. So I mean, is there any parameter space exist where the graviton exchange process is dominant compared to this one? I mean, there is a possibility, right? Because yes, because you are reheating. Yes. Okay. Because we have calculated that graviton exchange process, the mass turns out to be around this. Of course, that is depending on reheating, but it becomes pretty much of the order of, because this is for fermion, right? But for scalar rolls, your mass turns out to be 10 to the power 6 GeV.
Hi, Gregory. Thanks for the nice talk. So, so I know you talked about scalars, vectors, right? So my question is a bit unfair, but let me still ask. What about tensors? How will you do this for biometric gravity? Maybe it can be done. I just don't know. Yeah. Yes. Yes. Correct. But spin 3/2, this thing can be applied straightforward, right?
So on slide 19, so at this critical point, what is that? Some ATR in the middle? Yeah. So is your curve differentiable there? So this curve, it seems to, is it differentiable at that point? So it's like a sudden abrupt change? So is it fair to say that expansion rate would not be defined for this point?
Okay, I think we need to move on now. Let's thank Raghuvir again. Our next speaker is Arko Bhaumik. So it's 12 plus 3.
Is it a bit better now? Okay, sorry. So, okay, let me start over then. So let me thank the organizers once again for this splendid opportunity. Here is the title of my talk, which you have already seen. And this was done in collaboration with these two very nice guys, and it's due to appear on JCAP soon. So here is a brief outline of the talk. I'm going to give you a very brief recap of first order vectormetric perturbations. Then I'm going to present to you the possibility of having PMFs or primordial magnetic fields as a possible candidate to have sustained vector perturbations at the first order. Then I'm going to present to you the generic formalism of vector-induced gravitational waves or VIGWs. I'm going to give you the spectrum of VIGWs produced during a particularly stiff kinesion-dominated post-inflationary epoch. And I'm going to move on to some predictions for next generation interferometric GW missions. And I'm going to conclude by pointing out some future directions that we plan to explore in the near future. Okay, so first order vector perturbations don't quite often receive a lot of attention in the minimal, or better to say the standard model of cosmology, and that's for good reason. Because in the absence of a proper source which can generate vector perturbations continually, these first order vector perturbations, which are represented by this gauge invariant variable Vi, they tend to decay away very fast with cosmic expansion. And that renders them over time of negligible magnitude compared to their scalar and tensor counterparts. But things can be quite different if you have a source. And such a source can emerge possibly from the matter sector if we have a non-zero vector projected component of the spatial stress energy tensor that comes from, say, primordial magnetic fields, which are a particularly good candidate for generating such vector perturbations. So now, of course, a few words about PMFs. So over the last few decades, a lot of observational evidence has been amassed which indicate that our universe might be very weakly magnetized on very large scales. And while these PMFs on galactic scales, which are typically of the order of magnitude of the microgauss level, these can be explained on the basis of several astrophysical dynamo models, amplification mechanisms. These models are increasingly challenged on much larger scales, such as the IGM scales of 1 MPC and beyond, where we have these kinds of bounds currently. The lower bound comes from the non-observation of secondary GeV cascades, which should be generated from primary TeV scale blazars, and the upper bound is an indirect bound which comes from CMB and currently available 21 centimeter observables like the AGES report. That might be a bit dubious, but bear with me. So these initially reported an upper bound of the nanogauss order, but over the years this has been increasingly tightened to, say, an order of 10 picogauss or so. So right now we have two bounds, a lower bound of 10 to the power minus 16 Gauss and an upper bound of the order of 10 to the power minus 11 Gauss. And if we assume, the challenges that dynamo models face on these large scales indicate at a possible primordial origin for these magnetic fields. And if we assume a PMF, which is stochastic, non-helical, and Gaussian in nature, then it can be completely characterized in terms of its two-point function, which gives us a measure of the magnetic power spectrum. And on the other hand, the magnetic sector carries an intrinsic stress energy, whose vector projection gives us a suitable source term for sourcing first-order vector perturbations by giving us a source term on the right-hand side, which looks like this. So this pi IV is written in terms of the co-moving amplitude of the magnetic sector, and all the time dependence has been factored out in terms of this scale factor squared, which is sitting in the denominator. And this equation has a particularly simple, elegant, exact analytic solution, which was derived by Mack et al. Way back in 2001. So you can see that the entire time dependence of the first order vector perturbation, when it's being sourced continually by the magnetic sector, which decays as 1 by a square, the magnetic field, the entire time dependence can be factored out in the form of this eta upon a square term, a being the scale factor. And you can immediately appreciate something interesting in here, is the fact that the evolution of the first order vector modes generated by PMFs depends crucially on the time evolution of the background, because the scale factor depends on the conformal time as a function of the parameter W, which is the EOS parameter. So in general, stiffer the background, slower the decay of the vector perturbation. And in absence of any source, it just decays as 1 upon a square, as in the minimal scenario. And on the other hand, in case of the most extreme possibility, so to say, which is of a kinesion dominated background with W equal to 1, vector perturbations according to this equation, this eta upon a square can become time independent practically. So these vector perturbations are permanently sustained. So this is going to be a very interesting possibility to us, as we'll see in a moment. And before we get right into the heart of stuff, a bit of a foreword about induced gravitational waves. So IGWs very broadly can be interpreted as a direct consequence of the inherent nonlinearity of the gravitational field equations in Einstein's model. Because in such a model, lower order metric perturbations can act as source terms for higher order metric perturbations. And this has sparked a large body of research over the past decades. The most prominent spot being occupied by, arguably, by scalar induced gravitational waves, where first order scalar perturbations induce second order tensor perturbations. And apart from that, there are several other studies, not all of them are about IGWs. So this list is mostly about second order metric perturbations induced by first order metric perturbations. So you can have second order vector perturbations induced by first order scalars and so on. That being said, the possibility of having vectors, first order vectors, inducing second order tensors has been relatively little explored in the literature so far. And that is precisely the area that we wish to focus on in our work. So this right here is our general scheme. We assume the existence of a primordial magnetic field, which provides us with a spatial stress energy tensor that can act as a source term for sustained first order vector modes, which in turn can induce second order tensor modes. And these are what we refer to as VIGWs. So the usual starting point for that would be to have a generic bilinear source term for VIGWs, which is given in our case by SAB. This was derived using the expand package of Mathematica developed by Cyril Pétrou et al. And transforming to Fourier space in the helicity basis, we can immediately write, following from this equation, the mode function, the mode evolution equation for the tensor modes, where the helicity level source scalar is given by this a bit cumbersome looking function. So I need to point out right here, before I proceed any further, that there is nothing special, there is nothing specific to PMFs about these two expressions. So these are all about generic first order vectors inducing second order tensors. Thank you. And the input of a PMF, in fact, comes much later, which I will point out in due course. So we already have the mode equation right here. So now we are interested in solving for the mode function using the Green's function method preferably, and calculating the 2-point function of these H lambdas, which are going to give us the stochastic gravitational background. And from that we can obtain the energy, the spectral abundance, the spectral energy density of the GWs. So in order to do that, we have already noted that H lambda is proportional to S lambda. So the 2-point function of H lambda is going to be sourced rather by the 2-point function of the source scalar. And since this source is a bilinear function in the vector modes, it's going to be sourced in turn by the 4-point function of Vi. And since Vi itself is proportional to pi I, which is the vector projection of the stress energy tensor, it's going to be sourced by the 4-point function of the vector projection. And we can simplify this 4-point function in terms of the 2-point function via the weak expansion method. So this 2-point function is specified in terms of the vector isotropic spectrum. And it's precisely at this point that the input of a PMF becomes important if we wish to proceed further. Because we can model the vector isotropic spectrum if we assume the whole scenario to be driven by PMFs as a convolution integral of the magnetic power spectrum. So the calculation is a bit tedious. I have some reserved slides for that if anyone is interested. But for now, trust me. So this is the expression. And we can simplify this expression, compute the integral explicitly, and arrive at some approximate analytic form for this vector isotropic spectrum if we conveniently assume the magnetic power spectrum to be of the power law form, which is a conventional choice. So this AB and NB, these are the two primary parameters of a non-helical magnetic power spectrum, which originate from the underlying magnetogenesis model. At this point, we can link with some specific magnetogenesis model. In our case, we need the magnetic field to be produced earlier than the onset of the post-inflationary epoch. So we choose the conventional Rathore coupling model, where inflationary PMFs can be generated via the explicit breakage of the conformal invariance of the Maxwell action. So in that case, according to Kobayashi and Slot, the two parameters AB and NB can be recast in terms of the fundamental parameters H inflation and S, which is the non-conformal coupling constant of the Rathore model. The scale factor A inflation at the end of inflation can be computed according to this formula. So our total parameter space right now consists of the Hubble parameter, thank you, the Hubble parameter at the end of inflation, the total duration of the post-inflationary epoch in terms of the number of E-folds, the non-conformal coupling constant, and the background EOS parameter. And now, equipped with all these pieces, we are now finally in a position to be able to compute the VIGW 2-point correlation function. But before we do that, the observable quantity is not the 2-point function itself. It's the GW spectral abundance, which on subhorizon scales is related to the tensor power spectrum according to this formula. And the present day GW spectral abundance on scales which were subhorizon before the end of reheating can be related in terms of the spectral abundance at the end of reheating according to this expression. But this whole factor encapsulates the contribution from the relativistic degrees of freedom of energy and entropy. The scale at the end of reheating can be approximated according to this expression, which can be derived just based on the Friedman scaling of different components and so on. So the bottom line is that, the literal bottom line, the GW spectral abundance on small scales can be computed at the end of reheating and related to its present day value with a factor which is approximately of the order of 10 to the power minus 5. So now, before I present you with the numerical results, a few necessary approximations need to be elucidated. Because post-reheating MHD turbulence sets in during radiation domination, we might need to take recourse to MHD simulations in order to model the superhorizon part of the spectrum at the end of reheating in a more accurate manner. So to keep things analytically intractable, since this is just an initial study in this direction, we have focused for now only on the production of VIGWs during the post-inflationary epoch. So the time integral, this basically implies that the time integral runs between the end of inflation and the end of reheating. The momentum integral is relevant for only those modes which re-enter during that time. And larger scales are basically superhorizon at the end of reheating. And this basically gives us an accurate estimate of the VIGW spectrum on scales which were subhorizon at the onset of radiation domination. But what about the modes which were superhorizon at that time? So this might be a bit of a loose approximation for now, but we approximate it with the universal infrared scaling, which goes like this, k cube of 4 omega GW. Thank you. Just maybe 1 minute. So this admittedly may lead to an underestimation of the VIGW amplitude close to k reheating from the left, but we find nevertheless that a detectably large VIGW signal can be generated even under these approximations. So these are the numerical results that we have obtained corresponding to a particular value, a benchmark value of S equal to 2 for the non-conformal coupling constant generated during kinetic era. So W equals 1 and S equals 2, that leaves us with basically two parameters, H inflation and delta N reheating. In the left plot, we have fixed delta N reheating at two representative values of 10 and 14 and varied H inflation. I hope this is visible from the back. And on the right plot, we have just done the opposite. We have fixed H inflation at two benchmark values and varied delta N reheating. So we can see that with increasing H inflation, there is generic increase in amplitude and an increased F peak, which we identify with the scale at the end of reheating, the inverse of the co-moving horizon size at the end of reheating. And with higher delta N reheating, the opposite takes place with regard to F peak. The amplitude keeps increasing as is expected. In this plot, we have varied both parameters simultaneously in such a way so as to keep the amplitude nearly unchanged, but the peak frequency or the scale at the end of reheating, that keeps changing. According to this plot, it basically shows you as a heat map the dependence of F peak on delta N reheating and H inflation. And it is a bit difficult to arrive at an exact analytic form for omega GW, the peak value of omega GW, as a function of H inflation and delta N reheating, because both parameters not only enter the integrants in non-trivial ways, but also their limits. Nevertheless, we can compute these values. This should really be f peak at the peak frequency. So we can really compute these peak values of the amplitude at several benchmark points for H inflation, keeping N reheating, delta N reheating constant, and the opposite. And we can see that these follow approximately linear. And based on these relations, so this is in log, and here we have so this plot tells us that the dependence of the omega GW at f peak depends on H inflation in a power law manner, and the right plot tells us that it depends on delta N reheating for fixed H inflation in an exponential manner. So overall we can combine them and arrive at this approximate scaling relation, where omega GW at f peak depends on delta N reheating exponentially and on H inflation according to a power law form. So here is a summary of the key takeaways of this talk. So firstly, there are 4 key takeaways. So firstly, we have first order vectors which can be important when they are being sourced continually by a vector projection of the matter sector. When sourced by PMFs, these vector modes can be particularly sustained during a stiff post-inflationary epoch, with the extreme scenario being given by a kinesion-dominated post-inflationary epoch. And the secondary tensor modes can be induced at higher order from such first order vectors according to any, which is based on the nonlinear nature of Einstein gravity once again. And this VIGW signal that results from point 3 may peak at small scales and be potentially visible to upcoming GW missions, which are interferometer based. And this study is of course not quite exhaustive, because we need to be able to better model the spectrum of VIGWs during RD on one hand, and on the other hand we also need to be able to distinguish between the VIGW spectrum on the observational front from other possible sources of degeneration, which are PGWs and SIGWs and so on. So with that, I reach the end of my talk. So thank you all for your attention.
Thank
and
you.
If there are questions.
We have time for only a quick question.
Okay, so you have, there are two, so you have two sources. One is the usual electromagnetic field, the another one is the vector perturbation.
Exactly.
So what about this electromagnetic field itself?
Right, that's a very nice question. So I guess I have the opportunity to go to a reserved slide for that. So here's a comparison that we made between the, I guess we're asking for the first order tensor modes which are sourced directly by the magnetic sector. Yes. So for kinesion domination, these are some of the comparative curves for identical parameter choices between the first order vector modes and the VIGWs. So these are, sorry?
Okay, yeah, continue.
Yeah. So what we found was that during a kinesion dominated reheating epoch, a post-inflationary epoch in general, the first order vector modes for identical parameter choices remain subdominant compared to the VIGWs. And this in fact can be explained on the basis of 2 key observations. The first one being that PMFs themselves decay during any sort of cosmic expansion as 1 by a square, but VIGWs, as we saw, they are sustained during kinesion domination. On the other hand, the VIGW spectrum, as its convolution integral involving the vector isotropic spectrum, that receives basically the at each value of k, it receives contributions from all values of k between k inflation and k reheating. So this, on one hand we have a k integral, on the other hand we have an integral over time. So based on these 2 observations, we can sort of intuitively explain the dominance of the VIGW spectrum over the first order PMF generative modes, at least for kinesion domination. But that being said, for softer values of the OS parameter, we found that the VIGW spectrum decays very quickly because it depends in a quartic manner on the vector perturbation.
Okay,
sure.
Did I understand that you evaluated the spectrum at the end of reheating and just diluted as 1/8 power 4?
No.
When did you evaluate the spectrum eventually, omega GW?
We evaluate it at the end of reheating, and the value at the end of reheating is related since both the spectral abundance
so
and
are you focusing on modes which are greater than KREH?
Exactly. So we have approximated the supervised.
All those modes are above K greater than KRE.
Yeah,
KREH.
we have actually calculated it accurately for K greater than K reheating. So there might be some sort of this might not be quite accurate near the scale that we identify as the peak scale, but we already can see a sort of flattening
when we evaluate it numerically. So we are approximating it with the universal k-cube scaling that I talked about, but that might not be quite accurate, close to the peak, but that is something we intend to revisit.
So I'm a little puzzled about the contribution due to the vectors themselves. You know, in the case of magnetic fields, you break this conformal invariance and you boost their strength. Vector perturbations decay even during inflation. So
this is not during inflation.
Sorry?
This is not during inflation. This is being sourced during the post-inflationary epoch.
No, I'm lost. The vector perturbations themselves will decay at any time.
But that it depends at any time if there is no continuous source.
Okay.
So that's the point of this equation. So if you have no source, it decays generally as one by s. But it doesn't decay if you have a dimension dominated radiating epoch and if it is being sourced.
About the constraints of magnetic field. There's a paper by Rick Bureau which indicates some magnetic fields can leak those levels. Okay.
Yeah. That's true.
Okay, I'm sorry, we need to move on. Let's move again. So the next talk is by Birefringence.
The title suggests we will be computing the 4-point autocorrelation of U1 gauge field in the inflationary background mediated through the scalar and tensor fluctuations. So this is an ongoing work which I am doing with my collaborators P. Jishnu Sai and Professor Rajiv Jain from JDC, and I would like to thank the organizers for this opportunity for presenting this work here. I'll start the discussion by just giving a brief motivations on the cosmological correlators and the method which we are going to use to compute these correlations, which will be the Indian formalism, and both these things are almost covered in this yesterday's talks and everything, so I will be just going very briefly on this. Then I will go on to the model which we are interested in, which is the U1 gauge field in the inflationary background. Once we are done with that, we will go and compute the 4-point autocorrelation functions, and the cosmological diagram which we are interested in computing, this as shown, and this is, you can view it like there is some process happening during the time of inflation, and we will be measuring the correlations at the end of inflation, which is denoted by eta naught, and all this will be in the conformal timing. Then I will show some of the results we have at the current stage, and we will discuss the possible consequences of this. As I already mentioned, we will be working in the calculating the higher point functions, or the specifically 4-point autocorrelation functions during the time of inflation, with the hope that this can shed some light into the inflationary scenarios, whatever is happening during the time of inflation. And these kind of higher point functions are computed already for tensor and scalar perturbations specifically, but computing this for other fields like the gauge fields or other fields in the standard model will also be interesting. And specifically in this context, we are focusing on the U1 gauge field, and we look on whether these kind of 4-point functions can give us an intuition about the primordial magnetogenesis. Specifically, the models which we are going to use in this analysis will be the one which are simple ones which are going to use, which people are used in order to understand the primordial magnetogenesis, like the Ratra coupling. So with that, I will move on to the mathematical tool which we are going to use in order to compute these autocorrelation functions, which will be the just Indian formalism or the Schiller-Keldysh formalism. So this formula is also shown in this meet several times. This is just the way to compute the Indian correlators, and the things to note is actually the operators here are anti-time ordered and this is time ordered, and this will be the complete vacuum we are interested in. This will be the free vacuum with respect to which we are computing this thing. Just one more thing I just want to highlight is actually related with the calculations of this thing, and we have to keep track of the order of these things. The blue part
what I show is lives on the blue contour, which is a different contour from the red one, the time order things. Because this, if you are not keeping track of these things, this can cause various divergences in your analysis. This has been shown, and this will be there. Means, basically the point is we have to keep track of the contour properly, so that it will be going to the properly bunched Davis pattern. And since we are doing perturbative analysis order by order, if you are just going beyond some first few orders, things will get messier, and keeping track of this will be a bit tedious. And one good way to do that is actually using the cosmological diagrammatic methods, which is something we are going to follow in this analysis completely. So with that, now we are moving on to the model which we are interested in doing this analysis. This will be just the U1 gauge field working in the inflationary scenarios, and mostly I will be working in the conformal timing with this sort of metric. And since we are looking at the magnetogenesis, as we know that there is a very weak correlated magnetic field in the entire universe presence, in order to explain that, one of the good model is having a primordial origin. So if it has to be amplified, the standard Maxwell's magnetic field which we are interested in, that is conformally symmetric. So this has to be broken. Like for the amplification of this thing, conformal symmetry has to be broken. So the model which we are going to use, or sometime used, is actually the balatonic coupling or the kinetic coupling, which is called the Ratra coupling, and which actually explicitly broke the conformal symmetry in the system. And other more constraints we are actually assuming that the lambda will be going as a monomial functions of A, the scale parameter here, and which is actually given as this form in the terms of time, conformal time. So this model is several times explored in the literature, and we know quite a bit about these models. And one thing we know is actually for n is equal to 2 and n is equal to -3, this model is able to produce the magnetogenesis, required scaling rate and required magnetogenesis just using the inflationary scenario itself. And another things we know is actually for n is equal to -3, this model has problem, which is the back reaction problem. That means the energy density of the electric field starts growing, and it will outgrow the background energy density. So the perturbative assumptions will be broken. And for this n is equal to 2, there is no back reaction problem, but we have another problem, which is the strong coupling problem. And in the time of inflations, the coupling of electromagnetic field will be very strong, and that also breaks our predictive powers on this flow. So these two problems are there, but they have way around some of this problem, but still there. That means we have only two things, like the 2 n is equal to 2 and n is equal to -3 will be more interested to us also in our analysis also. Another thing I want you to notice is that there is no self-coupling for the gauge field here. These are just, there is no self-coupling since we are imposing the U1 symmetry intact. So the only interactions the gauge field can have is through the inflecton, which will be the lambda of phi here, or through the metric perturbations. And we are specifically choosing the co-moving gauge in this system, so which makes the system only possible interactions for the gauge fields will be only through the metric fluctuations or the metric perturbations we are considering. So once we set these things, next question we should ask is how this actually is interacting. That means we really need, in order to use the Indian formalism, we really need the interaction Hamiltonian at the order which we are interested in. So that's the next thing. For that, the one standard way to do that is this thing, ADM decomposition. Basically, we are foliating the space-time into space and time, and decomposing this into laps and shifts. And this laps and shifts as it's not a dynamical variable, constraint variable, which we can solve. This constraints equation can be solved order by order. This is the leading order solutions, and this will be the order which we are working here. And at this order, we can put this back to the action or the electromagnetic action when compute the interaction Hamiltonian at the cubic order, which is zeta A coupling with the scalar. Zeta will be the scalar fluctuations and gamma will be the tensor fluctuations, and this will be the interaction Hamiltonian at the cubic order, which we are going to work with. Yeah. Okay. So with that, the first thing one can calculate is the bispectrum, which is already calculated in the literature, and people have shown that there is actually log divergence. When eta is going to very small values, this will get diverged actually. But this is not a problem at this level, but this can be a problem if we are going beyond these things, and that's exactly what we are doing. We are going to calculate the Popon autocorrelation functions here. This will be the cosmological diagram we are interested in, and the complete set of diagrams by interchanging 2 and 3 kind of thing will be this complete spectrum. So we have to calculate this complete diagram values, and schematically the results will be like the Popon diagrams will be like this. We just have to compute this thing. This real part comes because you have to account for the mirror symmetry, reflection error of the line. So we have to compute. In general, the results looks like this for scalar and tensor decomposition, where Q's are the part where all the polarization is gone, polarization of the gauge fields and the polarization of the electromagnetic field, everything is encountered, and IAs will be the next time integral. And this will be same for all the non-trivialities for going from zeta and gamma will be encoded in the Q's, and all other things will be, all IAs will be same for here. That will be the next computation. And we computed this for different values of n and for different limits of case. And just to note that there will be spurious divergence if you are computing this individually, but if you are computing everything together, this will get cancelled. And I will now list some of the results we have here. Basically, if you just keep all the case arbitrarily, this will be a bit messy. So we will first look at the equisided quadrilateral. That means all case will have same magnitude. And now the A's are always the auxiliary fields. The things we are interested in, which will be the electric and magnetic field, which can be computed from here. And in this equilateral equisided quadrilateral, we can get a general expression like this, where these Q's are the quantities which encodes the information about the polarizations, and I's are the same. At this level, I's looks like this. It will be a function, just a polynomial functions of Q's, log and polydialog. All other things are same. It's polynomial functions. We have these things, and at this level, the quantities from the polarizations will look like the scalar exchange. One thing I would like to note is that there is only dependence of theta 1, 2 and theta 3, 4. There is no angle dependence between these things, and these diagrams are in the 3D, not a planar diagram. So once we set the Q, Ki kind of things, we can fill the categories in the 3D. So for this is scalar thing, and for tensor this will be bit messier, because in tensor case you will have the polarization coming from the gamma Ij also. So this won't be this close to this symbol expression. So there will be theta dependence for all the momentum. So this will be messy, but this thing what I wrote here is actually more general kind of stuff, because I can't get a very close. We can get actually, won't be very close like this, and pi's will be just like the projection tensors here. So this will be true for all the cases, and much more simpler limits which we can nicely see the results will be the countercollinear limit, where we assume that the exchange graviton or theta is going in the very IR, that means very low momentum kind of things. At that point we can write the Popon autocorrelations like this, just like in terms of power spectra of theta and beta, where there will be a constant kind of C, B and L kind of thing. Same thing for the tensor exchange. As I mentioned, for the tensor exchange there will be theta elements will be a bit complicated, but at this limit we can write like this way. And this kind of structure actually shows us there is in this equivalence way soft theorems for the Popon autocorrelations function, which themselves has their own interest. So with that, this is all for n is equal to 2 case. Whatever results I show now is for n is equal to 2 case, and now we will slightly extend to other n's, or I will just comment on the results for other n. For n is equal to 2, we see everything is finite. There is no problem coming up because of the expected divergence. This is true for all -2, 1 and 2. This will be fine. But once you go for the n is equal to -3, which is the another scaling, which is the regime where we are getting another scale invariant result, there is actually log divergence coming up. That means if you are going to eta not to very small numbers, this will start diverging up. So this regime is problem, and the same behavior pattern goes for higher values of n also. As we start increasing n, the polynomial and higher polynomial degrees of divergence as we go closer to eta naught tends to 0 limit, and this actually means that we have to check carefully about the perturbative validity of these theorems, because the first order corrections will be very finite, and as you go next order, this is actually getting divergent kind of things. And for n is equal to -3, we already know there is a back reaction problem. This also adds up to that. And for another, only other model which we have this scale invariant structure is n is equal to 2 case. There we have the strong coupling problem also. So yeah, that is it. That's a summary, and thank you.
Thank you. We have time for questions.
Is there a law
No.
The leading term, no, I'm not talking about A, more like probably, you are just calculating the B. There is no R involved here. I'm a little puzzled. Are you calculating R squared BB?
No, water correlations only. BB kind of, which is exchanged through this.
But then how are the interactions, higher order interactions arising? I thought you were calculating gamma R and BB.
No, just water correlation A thing, BB, then which is through the exchange. Interaction through gamma is happening.
How are those higher order actions arising, a fourth order A?
For cubic order only. No, quadratic order, our interaction is cubic order. Gamma AA or zeta A.
Okay, I'll speak to you separately.
There are no further questions. Let's thank Haridev again. We move to the final talk of the second session. Chandranathan Anand Vijayan.
Hello, I am Chandranathan. I thank the SOC for giving me this opportunity to talk about my work here. So the title of my talk is about reconnection-driven decaying energy turbulence, but a slightly more appropriate and simplified title would be this. So what I want to do is I want to talk about the primordial magnetized universe, but I'll put it in a box. Let's uncover what this means. But let's first understand whether or is our universe magnetized. This comes basically from observing gamma ray emission from TV blazars. So there is a subset of blazars which emit in TV, and they have a large mean free path, so they traverse cosmological distances, mostly through voids, and when they interact with extragalactic background, they pair produce, and these pair produced particles cooled by inverse Compton, and they produce secondary gamma rays, and this is what you expect to see in telescopes on Earth, like and CT in the future. But the story slightly changes in the presence of an extragalactic magnetic field. So if you have a magnetic field, so if this is like the intergalactic medium, mostly voids, field, and they can be deflected along the line of sight. So you will see as a result of this is that your primary GeV flux will be suppressed. That's first effect, which was shown by this seminal work by Naranov and Boak, that was in 2010. Sorry. So what you see here is that when Fermi was observing at the secondary flux, the upper bounds that they put is not consistent with models that do not include IgM magnetic fields. So that is the first clue. And the second thing that you would expect is that you would form a fainter secondary halo. This has not been observed, but people have done a lot of simulations of this. What you see on the right is that if you have a primary source and you put a IGMF, you expect to see a halo around the primary source, and people wanted to detect this. But very recently, last year, what they have detected is the when you look at a GRB, you will expect to see that this sort of halo emission comes after some time, and they claim to have detected that time delayed secondary emission. They called it a pair echo. So this gives us hints that the IGMF is magnetized, because other astrophysical explanations are not feasible. We think that these magnetic fields came from a primordial origin. So let's believe that this magnetic fields came from the very early universe. So then the question is, you observe them, yes, but how do you produce them? So you produce them in some very early universe process, say inflation and phase transition. Once you produce them, it evolves with the evolution of the universe, and that evolution is captured by decaying emission turbulence, because you have plasma and you have magnetic fields, so the correct thing to do is decaying emission turbulence, very collisional. And this happens till recombination, and post recombination there's flux phasing, so it just dilates with expansion. So if this primordial magnetic field exists, it has implications for a lot of physical processes that happen in the universe, starting with even at the level of production. If you could somehow produce helical fields, that would require a new physics that has to be put in. It could affect BBN, it could affect glass scale structure, it could affect CMB, and it also could serve as a seed for the galactic dynamo, which is also under debate. So in this talk, I would touch mostly upon the evolution part. If time permits, I'll very briefly tell us the work that we are doing with recombination. So the plot that I'm showing you here is the strength of the magnetic field versus the correlation scale. This is the observational bound that comes from Fermilab. So the initial conditions are as follows. Here I am considering that the initial condition came from electroweak phase transition. So what I would require to do this is that you give me a strength of the field and you give me a correlation scale. So here the strength of the field is, let's say, 1/10 of the energy of the universe. That's the energy that went into the magnetic field. And then the correlation scale is 1/100th of the orbital. So this is some conservative estimate. If this estimate is given and there is a endpoint which is given by at what time scales does the system evolve. This is the endpoint at recombination. So once these things are known, then this is how the magnetic field would evolve, and I will talk in detail about this particular line, how this evolution occurs along this line. That's what I talk about. So so now we have decaying turbulence. But how do we talk about decaying turbulence? Because it's a very complicated nonlinear interaction that goes in turbulence. But how do we talk about decaying turbulence? We follow Kolmogorov to do this. What we do is first we identify an ideal invariant that is better conserved than energy, and we assume that the decay proceeds by some dynamical time scale. For example, if you just take a cup of water and you stir it, you'll see that you'll form eddies, and the eddies will sort of like break apart and so on. So the eddy turnover time would be a dynamical time scale. So from now on, what I'll assume is that we are talking about some sort of peak spectrum, and I would only care about the strength and the correlation scale of the field. If that is there, I would assume that the decay proceeds by this eddy turnover time is given by L by U, and some sort of average angular momentum is conserved. That is what the conserved quantity for me would be. that is given by U square times alpha. If I put these two things together, it will just give me a scaling law for the energy and the correlation scale. Now what I have to do is I have to put universe in a box, stir it and leave it and see how the energy decays. So for this case of hydroturbulence where there is no magnetic field, I recover back the scaling laws that are calculated by Cosmology. Moving on to the MHD decaying turbulence, there is an additional component for when we talk about MHD turbulence, which is magnetic helicity. Magnetic helicity tells you how field lines are twisted and dotted. It's given by this expression. What was known already is that if you have helical magnetic field, they always relax to larger and larger scales. And since magnetic helicity is an eigenvariant and it also has presence topological constraint to the decay, your decay proceeds conserving this helicity. And what was known was also that if you don't have helicity, then also the field inverse happens. Now, what is the decay time scale in this process? What is the conserved quantity, and what is the reasons for this inverse transfer? So to study the time scale, we need to understand this process called magnetic reconnection. So magnetic reconnection is a process in which the topology of the magnetic field is reconfigured, and this is accompanied with the release of energy in the form of particle acceleration heat. Magnetic reconnection has been explored in various astrophysical contexts to explain high energy phenomena, including solar flares, gamma ray bursts, and cluster emissions, which was explored in our group. The model of reconnection that we consider is called the Sweet-Parker reconnection, also called the slow reconnection. And details apart, the time scale of this process of reconnection depends upon. So what you see here is that there are opposing magnetic fields, and between them there is a current. The current is like a sheet. It has a length, it has a width, and the reconnection time scale depends on the length and the width of the current sheet, and also the alpha velocity. So the reconnection time scale is given by this number S, and the alpha time S is called the Lundquist number, which depends on magnetic field, the alpha velocity, and the density. So what you're seeing here is a 2D system. A little bit of subtlety is it's a 2.5D system, but you're seeing contours of the AZ, the Z coordinate of the vector potential. What you're seeing here is that you see these smaller islands of magnetic field. They sort of merge in with each other, and then they form larger and larger islands. So this tells us that the decay occurs via the reconnection time scale, in particular the Sweet-Parker, which I'll show. And the conserved quantity here is the magnetic flux, which is an ideal invariant in 2D. So inverse transfer occurs because things are hierarchically merging to form larger and larger structures. And the same is true for the helical case. This is the same, this is the decaying turbulence in 3D. So it was already shown by Pallavi that reconnection is important when you want to understand 3D decaying turbulence. So here also you see that the magnetic field goes to larger and larger structure. Here it's not extremely clear that they are reconnecting, but it will be clear in this plot. Here I'm showing you 2D and a slice of 3D. The background is the current, and the contours here are magnetic fields. You'll see that between two islands of magnetic fields you'll form this very sharp currents, and things will start reconnecting and form larger and larger structures. So what's more interesting is that if you take runs with different physical parameters, which is the Lundquist number, and then you plot. So this is how your RMS magnetic field goes with time for 2D and 3D. But then if you rescale the time with your Sweet-Parker reconnection time scale, everything collapses on top of each other, and then there is the scaling law, which is the same way we use concept of prescription to arrive at the scaling law. And the scaling law is the same for 2D and 3D. 2D is better, 3D is, becomes better with larger and larger S, larger and larger Lundquist number. Same is true for the helical case as well. So this is a non-helical case, this is a helical case. So the punchline is that runs with different physical parameters collapse on top of each other when you rescale with the reconnection time scale, and so magnetic reconnection governs the decay of the system. And in 3D, the same conserved quantity is conserved even here, and the decay laws are consistent with this conservation, there's a huge exclamation here. So the point here is that 2D and 3D decay laws are the same, which basically means that 3D systems behave 2D in a very local sense. So the exclamation here is that some people might object, which is fair objection, that A is not gauge invariant, right? But what we believe is that 3D systems sort of conspire locally to give you the flux which is invariant, just like the 2D case. That's what we believe. And to understand whether these systems are locally anisotropic, we use these quantities called Minkowski functionals. So these are basically trying to understand the shape of any fields that you have in the system. On the right, I'm just showing you isosurface of magnetic field, isosurface of vorticity. But if you look at MST systems, what I'm showing you here is that there is a current isosurface and there are magnetic field isosurfaces in red. You'll see that this looks like a potato chips, and it's very 2D-ish like. And if you look around magnetic fields around this current sheet, they'll also behave in a very 2D-ish like manner, look in a very 2D-ish like manner. So using this, we conclude that 3D MHT systems are locally 2D and their dynamics is 2D. So we are trying to go beyond looking at just the time evolution and also look at individual modes in the spectrum. That is one thing that we are doing. And there are some challenges because we need to resolve the larger scale and also the smaller scale. So we need to look at we need to do a large resolution simulation. So the ones that I was showing you were 1024 cube, but we need to go beyond that as well. I'll take half a minute to just tell you the other thing that we are doing. So the other thing that we are also looking at is to see the effect of primordial magnetic fields on recombination. Very briefly, initially the plasma is very incompressible because photon pressure is very high. But then as the universe expands, the photon mean free path increases, and at some point it will become larger than the fluid scale. Now if there is magnetic field, it can compress the fluid, and the photon would just act like a drag there. So there will be compression, but there will also be radiative transport, which will transport photons from very high density to very low density. All of these processes could affect the recombination history. So this is some analytical work has been done by our collaborators. In the linear regime, we want to do the nonlinear problem and see what we get. So just to summarize, I'll leave the summary here. Thank you. Yeah.
Thank you. Questions? I had a quick one. So what is this 2.5D?
Yeah, so 2.5D is when you have all three components of the vector, but the spatial dimensions are x and y, in x and y, because helicity is not strictly defined in 2D, so you have to do the 2.5D.
So that is why you have the z component of the...
Nerenov and all, right? It's a local. It's based on an specific astrophysical environment, right? It's not a primordial limit. It's not a cosmological limit, right? Anyway, so my follow-up question is: are there any limits from radio observations or any constraints? Because again, you should get some synchrotron radiation also, right?
But synchrotron means that your field should be strong enough, right?
But you have a lower limit, right?
Sorry?
You have a lower, the Nerenov and...
Nerenov has a lower limit, but one of the science goals of SKA is to get, also look at this full IGM magnetic field.
So right now, the current radio observations are not sensitive
to my understanding, no.
So I can comment on something, just one. So Nerenov is definitely extragalactic magnetic field. It's a limit on the extragalactic magnetic field. Not the primordial, but the extragalactic for sure.
Yeah. So we don't know what the source of this extragalactic magnetic field is, so we believe it's primordial.
Okay, then let's thank all the speakers of the session, and now we break for lunch. We come back at 2:30.